the energy of that photon, which would be this or this, goes into the energy increase of the electron in the atom. Now you can go the other way. Say your omega now going that way. Say you change the sign. And I'll change the chair while I'm at it. If your omega now, if you change the sign, so that would then, given what I've just been talking about, that would correspond to an energy decrease in your system. And if you're talking, say, about an atom with quantum jumps, then that would correspond to your system going from UK to UM, but M is now lower energy. So the difference in energy, where does it go? Well, it would correspond to a photon being emitted, right, shot out, and the energy of that photon would be equal to the difference in the energy levels, M, well, let's say EK minus EM. So K is larger now, the higher energy. The electron falls to a lower energy, and the energy difference is made up by the energy of the photon that gets shot out. Right? That's what's being said here. All right. Now, as usual, this seems to be happening quite a lot. An important new topic opens up in the last few lines of not just the session, but the whole board. Seem to be jinxed. You know that word, jinxed? A series of bad luck events, jinxed by this. All right. Now it's sort of two topics, right? The energy-time uncertainty relation. So it's sort of Heisenberg uncertainty principle. Delta E, delta T that we're heading towards the next sessions, right? And something called Fermi's golden rule. Don't worry about what that is. It's coming up. So it's sort of two topics in being discussed here, introducing the concepts. Now that's the Fermi. Oh gosh, he's famous for so many things. Fermi-Dirac statistics in statistical mechanics. The fermion, it's the particle with half integral spin. The same Fermi or Fermi's, the Fermi paradox. That famous question about SETI, search for extraterrestrial intelligence. If life is commonplace, and trillion stars out there, and laws of physics, chemistry, the same throughout the universe. There are zillions of planets, so life is, water is very common. About a tenth of planets, water is liquid. This kind of reasoning. So therefore, life should be just everywhere in the universe. And a lot of these star systems are billions of years older than we are, than our solar system. So there should be hyper-intelligence out there that's commonplace. Well, if that being the case, why do we not see any evidence for these hyper-intelligent beings, billions of years more advanced than we are? And that's Fermi's famous question: where are they? So it's the same Fermi. Now if you've been following me consistently, you'll know my answer to that question is I call SIPI. Search for infra-particle intelligence. In one of the sessions, a few sessions back, I talked about this. I think these hyper-intelligent creatures will have figured out how to manipulate matter at the femtoscale, femtometer. It's 1,000,000 times smaller than nanometer. So they would not only have nanotech that humanity's starting now, they would have femtotech at the scale of quarks and so on. And if they can do that and they get smarter and smarter, who knows, maybe they will then go down to attotech, which is 1,000 times smaller, and then zeptotech, which is 1,000 times smaller than that, and so on, and maybe right down to the Planck scale. And that's as far as we know, humanity knows about conceptually in terms of our humanity's theories. And that's at 10 to the minus 35 of a meter. So maybe intelligence is everywhere, and these hyper-intelligent civilizations living in elementary particles. Sounds crazy first time you hear it, but it's logically coherent. It makes sense, right? Humanity's going from microtech to nanotech, and so the next step, of course, would be femtotech. There can't be picotech because there's nothing in nature between the size of the atom and the size of the nucleus, which is 10,000 times smaller. Sorry, 100,000 times smaller. So there's no picotech. And unless you had such huge femtotech-based things, components, when you put them together, you went up a scale of 1,000. I mean, that might be possible. But the underlying tech and the theory would be femto. Anyway, that's Fermi. So there's something in quantum mechanics called the Fermi's golden rule. Right? Now, what's really significant about this, and we're just leading into it now, is that here, this graph here. I was saying in the previous session, the peak is not infinitely thin. I mean, it gets very thin because its height goes as proportional to t squared, time squared, and its width is proportional to 1 over t. So it's not a delta function. It's not infinitely thin, and so that means, if you think about it, that the energy difference between the state, if your k is your starting state, uk, then there's still a probability of a transition occurring, even though the energy difference is not exactly due to the difference between these two. Now, maybe that's not so clear. Maybe it'll clear up a bit in future sessions. But what I'm leading to here is that the classical mechanics law of conservation of energy is not strictly applied in quantum mechanics. So in a sense, it's possible for a quantum system, it's hard to choose the right words, in a sense to borrow, if you like, energy from elsewhere, and then in a sense pay it back within a certain time, delta t, and so the amount of energy borrowed, in other words, the amount of, what's the word, violation, the level of violation of the conservation of energy law, delta E. There's a missing energy, if you like, delta E. So long as that delta E times delta T, so long as the energy is paid back within that delta T, then and such that delta E delta T is of the order of Planck's constant, then this delta E delta T form of the Heisenberg uncertainty principle, HUP, that we're heading towards, then it is allowable. Quantum mechanics seems to work that way. And you get, in fact, some people think our whole universe is due to an energy fluctuation of this kind. And then it just expanded and expanded, especially in the very, very earliest moments after the Big Bang. We got inflation, when the universe increased its size exponentially over time. So, some people talk about quantum cosmology, our whole universe as a quantum state with superposition and fascinating stuff. And so our whole universe, us, may have resulted from a quantum fluctuation where this delta E just came out of nothing. We came out of nothing. Now the philosophers, you can imagine the philosophers having a field day with this. So, there have been a lot of philosophers dealing with the philosophy of quantum mechanics because there's a huge number of deep philosophical questions come out of the interpretation of quantum mechanics. Unfortunately, quantum mechanics itself, in terms of field theory and quantum field theory and topological quantum field theory, it's getting harder and harder, and so there are fewer and fewer, being blunt, remember I'm PR, not PC, there are fewer and fewer philosophers who have enough mathematical intelligence and the knowledge, they lack the knowledge at these highest levels in pure math physics, to be able to have sensible discussions on the philosophy of these, these latest versions of quantum mechanics and topological quantum field theory and so forth. They just don't have the knowledge. And increasingly they're also being weeded out, even if they made the effort, which is considerable, as you know, if you follow me for years, you realise how much effort's involved. But so they know they have the knowledge, and progressively, as it gets harder and harder, these academic philosophers will be weeded out, right? They just won't have sufficient mathematical physics nous, IQ, to cope with it. And so in practice, you're finding now that the philosophers have almost given up trying to philosophize about the philosophical consequences of these weird latest quantum mechanical ideas. Anyway, well, forget about Fermi's golden rule, that'll come later, but this energy-time uncertainty relation, it will follow from the finite width of this graph. It's not a delta function, it's not infinitely thin. So you can get transitions that are not exactly equal to this, right? So the transition does not occur exactly at that value. It could occur, anywhere in this width. So you don't get strict energy conservation as a consequence of that. And I'll be talking a bit more about that in the following sessions. So brace yourselves, be prepared to accept the idea, well, at least be aware of the idea, that in quantum mechanics, conservation of energy, one of the basic fundamental assumptions of classical mechanics, conservation of energy is not strict. It's a big deal what I've just said. There's a Heisenberg uncertainty principle form that delta E delta T is of the order Planck's constant, h bar. And I will get back to you on what the delta T means, how to interpret that. The uncertainty in the time at which the measurement occurs, maybe something like that. It's been a while since I've studied that, so I need to refresh myself. Okay, until next session.